Good morning. Welcome to Krishna's classroom. Let us briefly recall where we stand at the moment. We have systematically introduced Lebesgue integral and come up to the class of measurable non-negative functions. Okay. And now we are just exploring the properties of the integral we have introduced for such class of functions. Now this has been achieved in stages because we started with what are called what you call simple functions. That is a step, and where we defined what Lebesgue integral is. From there, through approximations, we went to the next step, namely defining Lebesgue integral for what are called the bounded measurable functions on sets of finite measure. So there were a lot of extra tags on it, namely it is bounded measurable functions first of all. Secondly, the space on which we are integrating was also of finite measure. That is a restricted class. Now, after that, we go to the next step. As I had described earlier, we would have loved to go straight away to measurable functions. But then there are some catches for that which we have explained. So we first do it for what are called non-negative measurable functions. And this is what we have introduced in the last couple of lectures and explored. And now what we are doing is looking at some of the properties, especially now we want to look at what is called the linearity and monotonicity properties of this integral. But there is a word of caution. You go to the next step of dropping this non-negativity. Then only the process is going to be complete. This is only a partial step to mount to that position. We make use of what is called the linearity and monotonicity properties that we have proved in the case of the Lebesgue integral for bounded measurable functions on sets of finite measure. And as you already know that this more general class of functions, that is measurable non-negative functions, are approximated using those functions. So we exploit that result and then try to work out the results for this. Of course, as I go on, I'll explain that it's only a partial linearity property that we are to do, as we shall see. So we take this here. Give the statement. Let be non-negative measurable functions. Where E is a measurable subset of R. Then for any beta positive, integral over E alpha F plus beta G is equal to here we insist on both alpha positive and beta positive because we are working with non-negative measurable functions, and to ensure that alpha F is non-negative, because that is where we have defined everything, we need to assume that alpha is positive. Because alpha equal to 0 is a trivial case, beta equal to 0 are trivial cases. Moreover, this is the partial linearity part, and then monotonicity. You know that the function that the integral defines is actually a function on these class of functions. Now this function, what we are saying is that this function has the partial linearity property. Let me call it for the time being because of these restrictions, and what you call the monotonicity problem. Okay, so that's what we are trying to prove in this theorem. So we shall prove this theorem proof. So we first prove sort of partial homogeneity. Homogeneous. Okay. For alpha positive, what we want to prove is this, that is alpha integral of that is the first thing there. Okay. So for that, first observe the following. Observe that alpha F positive if and only if positive. Okay, that is because of this condition that that's the reason. That's one thing that we observe. Secondly, for alpha positive, let H is a bounded measurable function definite bounded measurable non-negative. Yeah, finite. You know what you mean by finite? That is outside a set of finite measure, the function is zero. Then we know that this is if and only if so this is the condition. So now we use the linearity on these class of functions which we have already. By linearity, of the integral on functions of bounded measurable functions with finite support we have proceeding to the integral over E of alpha h is less than or equal to integral over E alpha f, and this is of course if and only if integral over E of h less than or equal to integral over E of f. Now proceeding to the limit, what we do is we now proceed to the limit. When you proceed to the limit, you get the integral of we have proceeding to the to the supremum. What we have is at this stage we can write integral over alpha h. Proceeding to all functions, all bounded functions h with finite support we obtain integral over E alpha f so this is how it works. We have integral over E alpha h go to take the supremum over h, then this gives you and the equality remains, and what you get here is the same as taking supremum over here over h. This gives you alpha times this is what happens. Therefore, we have proved the homogeneity. Now, to prove linearity, we need to be integral over f plus g. This is equal to integral over E f plus, or we choose, that is we take alpha equal to 1, beta equal. Then combining with the homogeneity property, you get the partial linearity that we are working on. Okay. That is, we prove only additivity. So how do we prove this? Let bounded measurable functions with finite support was non-negative. Support such that K then what we have is h plus k is also a function, a bounded measurable function with finite support such that f plus k. Now, from the linearity of integrals, of the integral, on bounded functions to finite support, we have integral over E f h plus integral over E k h plus k and now proceeding to the supremum. So proceeding to the okay, we obtain integral over f plus integral over k is less than or equal to integral over and it is not equality that remains here because we are now proceeding to the supremum over this class, proceeding to the supremum over this class, and you know that in general we are talking about a subclass of functions of bounded measurable functions with finite support less than f plus g. Now h plus k is the class that which we are working on, and that automatically leads to this one. Therefore, this is what you. So that completes one inequality. So we save this in. Now we have to get the reverse inequality. We have to this is the next step. So how do we work on this? So we start once again, go to the basics, like the functions that approximate to f plus g, and then construct suitable functions which approximate to f and approximate to g from that. So let us do that. Okay. Or all L sorry L where L is bounded, measurable, measurable with finite support such that L okay. Now our strategy is to construct the following expressions. We construct bounded, measurable, functions h and k with finite support from L, F, G such that let us do it as follows. Now define H to be minimum of Fn. Now, since L has what is called finite support, on that cell H is on that set H is going to be 0. So H is also with finite support. Okay. Otherwise, if the value of F at a point is less than that of L, because L is something that supports F plus G. So it can exceed at points the value of F. Okay. So at those points F will be the H checks will be equal to Fx. Okay. And now K you define as L is of having finite support, H is also having finite support as we have described here. Therefore, K also has finite support. They are measurable, they are bounded, so everything is fine. Okay. And now we have to see whether K satisfies this property. So here you see that here now this is something which we have to verify. This is so. Note that this is something to be verified. Note that H has bounded, measurable, and it's the set on which H is equal to 0 may be as large as the support of L. It's not bigger. Okay, so that is there. That is easy to show. That is support of H certainly contained in support of support contains support of it. So at least it is as large as support. So it's a finite support. The second aspect is that 0 less than or equal to h less than or equal to f. Trivially, now what about k? K is bounded measurable and has finite support. Why it is finite support? Both L and H have finite support. So it's not just finite. What more? Now we want to prove that the following. So note that if Lx is less than or equal to Fx, then Kx equal to 0. Kx equal to 0. That means Kx becomes Lx minus Hx becomes Lx. So that's what happens. Okay. Therefore, for such x, Kx is less than or equal to. Now, if Lx is greater than Fx, then Fx, which is less than or equal to Tx. Okay? Then it implies Hx is less than or equal to so that is something that it's a supporting function for G. Thus, both H and K are bounded measurable functions with finite support and L is equal to by linearity of integration we have K, which is by definition is less than or equal to now taking we get therefore we have proved both the inequalities and so together we obtain integral over E now all that you need is to use using the homogeneity, combining with the homogeneity you obtain the linearity or the what you call the partial linearity. So that completes the proof. Now we prove the monotonicity. That's pretty easy to prove because suppose f is less than or equal to g, therefore suppose you choose an h which is less than or equal to f, where H is bounded measurable with finite support. Further, H is less than or equal to G. Hence, taking supremum, all such H you obtain over E because we are not possibly taking care of all the functions, all the bounded measurable functions with finite supports that are less than or equal to. There might be more functions than this class because of this inequality. That's why the inequality will. Okay, so that completes the proof. Now we prove the next theorem. That is, this is additivity over integration. So let a non-negative measurable function on D. Let A, comma B be measurable is empty. Then integral over A union B very simple to prove. It again, all the time we are going back to the approximating functions using the corresponding property of the approximating functions and number. So for any bounded function with the finite support H on E, we have this we have to now proceed to the limits. So you see that so also we have E naught is a of measure 0, then because A you take as E naught, B you take as now observe that integral over E naught F that comes. So we have proved both linearity and monotonicity. I think we stop there today and go to some of the convergence results in the next 1 or 2 lectures. Okay. So thank you very much.